Good, we're here. All right, let me just time this out. All right, hello everybody. My name is Jose, and I'm going to be presenting our work about Pixelweave Chromascale, which is a GPU accelerated pixel format conversions for efficient real-time video streaming. This is a work made by Evercast, which is the company I'm working for right now, but it's also partly done by Bruno Sena and Damon Stollers, who is here with us. All right, so a little bit about me. I am a computer science engineer, did a PhD in computer graphics from University of Pau in France. Right now, leading the engineering team at Evercast. If you don't know what Evercast is, it's a real-time collaboration software with secure video conferencing and high-resolution, color-accurate content streaming. So it's basically a real-time conferencing solution that also integrates high color and accurate streaming, basically used in the M&E industry. So our client is Hollywood, and the software is used for editing movies remotely. So it sounds fun, but it's actually nerds doing nerd stuff. So I'm also a professor at the University of República of Uruguay. I am from Uruguay, South America. So I also teach over there, and also just a little propaganda here. I also I'm doing co-chair of the RTC conference in Chicago on the research track. So in case you have some paper about real-time stuff and you want to submit it for this year, that's the QR for you to follow. Motivation of our work. This is a real simple overview of a real-time streaming service. I'm sure you probably have a lot of details to add to it, but this simplified version basically tells us that there's a video source that we want to stream in real time to the other side of the world or to the other side of the city or whatever. But in order to do that, there are several steps in the middle. First of all, and this is the main motivation, you need to do some kind of pixel conversion or scaling or rotation or cropping into the video, right? Then you feed that into the protocol, which can be WebRTC, and has an encoder, goes into the network, then it's decoded and it's rendered in the other side. So, for example, the video source in this context, or in the context of this conference, typically it's a webcam. But in our context, in our use case, it can be a Blackmagic or a Decklink, which are devices like capture devices that allow to deal with video, high quality video. It can also be an Asia device as well, or it can be a network protocol like NDI or SRT. So we're feeding video coming from the network into the system. So this side of the whole stack could be, as I told before, like resolution modification, chroma subsampling on RGB. So let's say maybe you're getting the video in RGB format, but you need to fit it in YUV. So you need to do that conversion, and even bit depth, you may be getting the video in 12-bit or 10-bit for each channel, but you want to fit it in 8-bit, for example. So you need to do that conversion. And there's even interleaved formats that are even more complicated to handle. All of this, typically, if you use WebRTC in the browser using Chrome, it's all solved already for you. But since we are doing a system that is native C++ code, and we want to really optimize the system, we need to deal with these things in a really fine way. So then this is fed into a real-time protocol, which can be WebRTC or it can be SRT, NDI, and then the encoder can be anything of the modern encoders. This is going through the network, and then on the other side is decoded with the same protocol, same decoder, and then needs to be rendered into the output monitor. Typical rendering here is rendering into the monitor using GPU libraries like Direct3D, Vulkan, or OpenGL. In a Chrome browser context, it would be the Chrome implementation of the rendering on HTML5. In our case, in the native application, it would be a Vulkan renderer, or it can be an output device, as the ones I was telling you, like Decklink, which would be like a board that you have right to your computer. You are outputting the video through it, and you have, like, for example, a reference monitor connected to it, where you want to evaluate the content in a really color accurate manner. So that you plug the monitor through STI or HDMI, and you want to output that to the monitor through the link. So the problem that we find in this context is that the encoders typically support a limited set of pixel formats, right? For example, libpx, which is the standard implementation for BP8 and BP9 from Google, support only these formats down there. So the video frame, you need to input it in I420 or YV12 or NVY2, and all of these have different layouts. But if you have video in other formats, then in order to send it to the encoder, you need to transform it. For example, the video sources coming from the Decklink SDK are all of those. And we can see that there are some of them which are in the BPX, but some of them that are not. For example, 12-bit interleave formats in RGB, or even 10-bit YUV. So what we found implementing this kind of system is that the process of converting one format, let's say one 4K frame in real time, 24 times a second, into the format that libpx requires is highly consuming, okay? So we have to check out how to do this efficiently in order to maintain the real time that we need. So how to make the video sources and things compatible? The solution is to use a per frame pixel format conversion that can also include scaling. How to integrate this conversion in every application? So basically, how to use one of these conversions? Well, please do not code this conversion yourself. It's quite a difficult task to do because it implies dealing with bitwise operations and these kinds of things. So use pre-built libraries, right? That's the solution that everybody uses. And for example, if you go into the source code of Chromium, there's going to be a library re-implemented for you that does this for you. So for real-time streams, well, it is computation intensive to do 4K 10-bit frames, 24 times or 30 or even 60 times a second, okay? So what the libraries that are the state-of-the-art libraries are using is using hardware acceleration. In particular, all the libraries that we've used are CPU-based, and they use CPU hardware acceleration based on vectorized operations. So for example, libswscale is one of the industry standards for this. It's part of the ffmpeg project. It's an open source library. It does image scaling, color space transformations, and pixel format conversions. But it's used by ffmpeg, by OBS, by libVLC, and it's CPU based. libyuv is the one that is used by Google Chromium. It's basically a set of functions for working with YUV formats, so YCbCr pixel formats. And it also supports rotation and cropping, which are things that are typically done and used in the smartphones context. And it's the one that is using libWebRTC. So if you're using WebRTC in Chrome, you're probably using libyuv. And it's optimized through SSA3, Neon, MSA, or RGB, depending on the hardware architecture you're running on. The third industry standard here is zimg, which is a project-independent library. It also uses vectorized CPU operations, but it has a wider core space support that is particularly useful for HDR workflows. And it's also used in ffmpeg right now, depending on the pixel format that you choose. And it's particularly optimized for Intel architecture. So those are the three typical libraries that one would use in this context. They're all CPU based. And moving forward, the scope of our work is to develop an open source library that does these pixel format conversions and scalings, but on the GPU. Why the GPU? Well, because the CPU is typically already busy doing, for example, encoding of the video, and the GPU in modern computers is there waiting to do something. And the pixel format conversion is also an operation that is highly parallelizable, right? One can deal with pixels in each thread at the same time. So the question is, why not? Why not using the GPU for this? And what we decided is to do an open source library that solves this, that we are using in our system, but that is available for anybody else to use and to improve. So there is some other software that do conversions like this on the GPU. For example, video editing software use pixel and fragment shaders when it's doing rendering to do this conversion. There's also the OpenFX image processing standard that uses CUDA for NVIDIA graphic cards to do this conversion. Also, DirectX 12 and Vulkan have their corresponding API for video processing. So all of those support doing some pixel format conversions, typically in the context of rendering. In our case, we don't necessarily want to render the content on the GPU because we're just streaming it. So we want to do the conversion and then just send it through the network. And this network processing is always done in CPU. So after studying a little bit, to our knowledge, there was no standalone GPU-based library that allows you to perform this kind of conversion. So that's why we decided to implement our library. So the library, we call it Pixelweave Chromascale, all right? It is right now a C++ library. It is designed with an agnostic multi-platform mindset and is based on an implementation-independent C++ interface of exportable functions. We have an example over there of how we will look to use it. So one creates a device which will select the GPU that you want to use, and then you just wrap your frame that you have on the CPU, you transfer the data onto the GPU, then you call the conversion with different parameters, meaning, for example, different resolutions or different pixel formats, and then you just retrieve the results from the GPU and you use it to send it to the network. So as you can see, this is a C++ interface. It is implemented completely using Vulkan, which is a GPU rendering library that is multi-platform. So we can use Pixelweave in basically any system that supports Vulkan. Right now, we're using this on our native applications on Windows and Mac, but it could be used in Linux, in Android, in iOS. We support a wide variety of color formats, of pixel formats. It allows, like it's listed over there, all the formats are supported. It allows scaling and range conversion and color matrix selection. Color matrix selection is, for example, when you want to do YUV conversion to RGB, and you can select 709 or Rec 2020, depending on if you're using an HDR or an SDR workflow. So we support all of that, and we support to convert from any of these formats to any other format. So the way we deal with memory management is we put a lot of work into making this as efficient as possible, because of course working on GPUs in video is always expensive in the memory management. One has to transfer the video frame into the GPU, then modify it, process it, and then transfer it back to CPU if you want to send it to the network, or render it into the screen directly. So the way we do this is using the Vulkan memory allocator that speeds up transfers, and we use staging buffers that yields the best overall performance, at least in the tests that we did, which imply both integrated and discrete devices. So that means that we tested this in NVIDIA AMD cards, which are discrete devices, but we also had tested this in integrated devices like those in the Intel CPUs or the M1, M2 of Apple. So in order to do the conversion, once we have the video in the GPU memory, what we do is we use compute shaders to do the conversion. There's a nice picture there that explains a little bit how it works, but basically we have a problem that can arise from the different sizes of the input and output image and the different pixel formats and chroma subsampling. So in order to be able to have each of the GPU threads work independently, what we do is we define a minimum work unit of 2 by 2 pixel blocks, and we let each GPU thread read that 2 by 2 pixels, so those 4 pixels, and do the work and write into the output images either 1, 2, or 4 pixels, depending on the chroma subsampling that you're choosing. Also, the work group sizes, which is something important for compute shaders, are determined by the output image resolution, so that the scaling filters do not result in additional memory writes. So we evaluated this library in two senses, in performance and in output quality. Why output quality? Because if one thinks about this is just a library that is converting one pixel format to another pixel format. So why would it be more quality to another when compared to another library? And the question or the answer to that is that the typical CPU-based encoders have what is called a real-time mode. Like, for example, I put here a little screenshot from the WebM. WebM is the ones that, for example, implement libpx for BP8 or BP9. So what they say there is that if you're using the real-time mode on BP9, for example, the results will vary from machine to machine and even from run to run, depending on what else you're doing. So that means that the encoder is actually looking at the CPU and is trying not to overflow it. So it will do a worse compression if you're doing a lot of things on the CPU, right? And that, for that reason, moving this pixel conversion, which can be highly consuming, to the GPU will leave the CPU a little bit more free to do the encoding in a better way. Okay, so that's why using Pixelweave in our cases, in our tests, shows that the encoding actually results in a better quality. So for the performance evaluation, we did we take Windows and macOS as two different platforms. We do their test on that. In Windows, we use a high-end NVIDIA GPU card. On macOS, we use the M2 CPU, which has an integrated GPU. We do two different pixel formats conversions in those contexts, and we do different resolutions. We measure the time for each frame, and for each of the conversions, we also measure the time of device copy, so memory transfers basically, the actual kernel execution inside the GPU, which is the one that is actually doing the actual pixel conversion. All right. So we can see how on the case of the NVIDIA GPU, which is in the Windows a discrete GPU, the memory transfers are a little bit more expensive, or are even more expensive than the actual kernel execution, which is the orange line. While on macOS, because it is an integrated GPU, the copies are really fast, but the kernel execution is a little bit slower because it's a much smaller GPU. So if we compare, we perform a comparison between the 3 libraries that are being used by the industry right now with ours. We use 3 different sets of, or set of videos, typical video samples used to do these comparisons. Big Bang Bunny, Ducks Takes Off, and Tears of Steel. We do the comparison in both Windows and macOS with the same computers as the previous one. And we can see how Pixelweave outperforms the other libraries in 3 cases. There's also some cases where the other CPU-based libraries perform better. This is basically because they don't have to do the memory transfer, which we do have to do. But in any case, what we observed is that depending on the pixel format that you're working on, there are some of the libraries that work really well and some others that work really bad, right? And so the result is that we have 3 different libraries to use, and they're really unstable depending on the pixel format that you're using. Pixelweave, which is our implementation, it's rather stable. So if it is not delivering the best performance, it is at least really near to it. So that means that if you use Pixelweave, you're ensured to have a rather stable performance, regardless of the pixel format that you're working on. We're talking about in the order of tens of milliseconds for each frame conversion. So in the results, in the quality results, we can see how integrating Pixelweave into the encoding process allows us to have more FPS in the encoding side, because we take computation away from the CPU and it leaves the CPU to do a better encoding. And we compared the produced images using PSNR as a metric, and we can see how Pixelweave provides the best accuracy or the best quality on the output image. Again, this is because we are moving computation away from the CPU and leaving more space for the real-time encoder to encode better. So conclusions from our work, Pixelweave Chromascale is an open source library, allows to do pixel format conversions, and it's open to contributions in GitHub. You can follow that link and access the code base and contribute to it, or use it as you need it. Our experimental results show that traditional CPU-based libraries are costly and can conflict with other tasks running concurrently. So for future work, we would like to implement color space conversions on our library so that we can not only modify the pixel format, but also, for example, do a conversion from SDR to HDR, or do a gamut or gamma conversions, even do tone mapping in the cases that could be needed. And then another interesting future work would be to provide memory hooks to use pre-allocated buffers. This would be in the context where you, for example, receive a frame from the CPU, from the network. You want to do the pixel format conversions before rendering it. And in that case, you probably don't want to do the conversion, then go back to the CPU, and then again send it to the GPU to render. You just want to have it on GPU, do the conversion, and then do the rendering. So for that purpose, we would need to kind of provide the pointer to the GPU buffer so that it can render it directly. And the same could be done from the encoding side, where if you already have the video on GPU, you can just do the pixel format conversion directly without having to transfer it initially. So a few references that I put throughout the presentation. So thank you very much.
Amazing presentation. Do we have questions for Jose? I see a couple there.
Okay. So when you're measuring performance, if you're doing the conversion on the GPU, there's some pipelining going on. So were you measuring there just the wall clock time from the CPU? Because it seems like if you're doing loads and loads of frames, I don't really care about the wall clock time. I care about how much work can I overlap and offload from the CPU.
Well, in the real-time context, we don't want to queue frames. We want to process each frame independently and deliver it instantly. So we don't have like a queue that we can say, okay, we have 10 frames and we work on them and then we send them all together. We're sending it one by one. So we need to have one frame latency.
Right, okay, so there's no pipelining.
Exactly, no pipeline, it's directly.
So I was wondering whether there are encoders, maybe not for VP9, but for H.264 or something, which work in the GPU and that you could like do the same memory trick of just keep it in there. Have you found an example where that would work? Because it'd be really interesting.
Definitely, definitely. And actually there is AV1 and BP9 implementations for the GPU. Actually, even Vulkan, which is this rendering library, now has a video module that can do encoding on the GPU. And definitely that could be a good thing. I mean, it could be a good thing in the sense of we save the memory transfer, right? So we have the conversion on the GPU and then we feed it to this library in the GPU. But it could be a disadvantage in the sense that the GPU would be doing more processing at the same time as our conversion. So now we are moving everything to the GPU and we're leaving the CPU alone. So that's kind of, but if you have a big GPU, you definitely can do that. And it's definitely going to be faster than doing CPU side encoding for sure.
You've mentioned Vulkan is used, and you've showed the performance for Mac OS. Do you use separate metal implementation, or you have some?
So Vulkan is compatible with macOS through a metal implementation that is already native. So if you use Vulkan on macOS, you're actually using metal on the backend.
Okay, thank you.
Thanks, interesting presentation. I'm wondering if you're looking at batching up like different streams. So you basically, instead of queuing like multiple frames from the same stream, what you can do, you can queue frames from separate streams. This way you can much efficiently use your GPUs because usually you have...
True. Yeah, that could definitely be a use case. It will allow to load the GPU much more, especially if it's a big GPU. You could load it with several streams and have every transformation being done in parallel at the same time because you have thousands of GPU cores to be used. So definitely that could be a use case.
Other questions for Jose? Okay, thank you very much.
All right, thank you.